AP Computer, AP Calculus BC, Unit 6, Day 9, the pretest review for the test that's coming up. So there's two parts that kind of match sort of the two parts of the test. Okay, so some float fields. I'd set it equals 0, figure out where the zeros are. 0, 0, 0, 0, 0. Maybe some symmetry. Well, the thing is, it only depends on y. It doesn't depend on x at all. So if y is 0, slope is 1, 1, 1, 1, 1. If the slope, if y equals 2, if y equals 1, slope is 2. Up 2 over 1, 2 over 1. Okay, if y equals 2, slope is 3. Up 3 over 1. If y equals -2, the slope is -1. There you go. Doesn't have to take a long time, this one. Where z equals 0, and y equals -x. So that'd be along this line. A bunch of 0 slopes. 0, 0, 0, 0, 0. 1, 0, the slope is 1. 1, 1, the slope, 0, 1, the slope is 1. -1, 2, the slope is 1. So you start to see that you share all these slopes on these diagonal bands. If you plug -1 in, you get -1 slope. You plug in 0, -1, you get -1 slope. So this is like a slant asymptote because they all go right into each other. -1, -1 is going to be a slope of -2. 0, -2 is a slope of -2, -2. -2, -1 is a slope of -3. And this one's probably -3. And -2, -2 is going to be a slope of -4. 0, 2 is going to be a slope of 2. I bet this one's 2, and this one is 2. 3, 1, 2, 1 is a slope of 3. 3, 3, and this is a slope of 4. So there we go. Where does this one equal 0? Well, that's going to be x equals 1/2, which isn't really on this graph. So, because that'd be between these. It should look like that at least. But there might be some kind of symmetry sort of about this line. This is where the 0 slopes would be, but we're not going to put those. If we put 0, 0, it's a slope of -1. If you put 1, 0, 1 here, 0 for the x, 1 for, okay, so you might notice this depends purely on x, doesn't matter about y. So if x equals 0 here gives you -1, x equals 0 here is also going to give you -1, -1, -1, -1. And over here, if you plug 1 in, you get a slope of +1, +1, +1, +1. So there's like symmetry. There's also these common lines, and it looks like it could be 0 in between here. So that kind of makes sense too, right? If you plug 2 in for x, it's going to be a slope of 3. 3. Plug -1 in, it's going to be a slope of -3. -3. And if we plug -2 in, it's a slope of -5. So that's a lot steeper. So there we go. Next one, where does it equal 0? Well, when x equals 0. So that is here, 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 here. And then undefined, technically we shouldn't put these on the slope. Division by 0 is going to be when y equals 0. So we put them here. They really shouldn't be in the picture. So but there's probably also some kind of symmetry. 1, 1, slope of -1. 2, 2 has a slope of -1. -1, -1 has a slope of -1, -1. So on these diagonals, -1, 1 is going to have a slope of +1, +1, +1, +1, 1, 2. X is 1, y is 2. So it's negative 1/2. So down 1 over 2. This one's probably up 1 over 2. This one's probably up 1 over 2. This one is down 1 over 2. You're also starting to see this is probably kind of like a circle or something solution. 2, 1. X is 2. That's going to be a slope of negative 2. And that kind of matches this. This is positive 2. So if you do one wrong, it should kind of stand out. Technically, we shouldn't have these. So maybe we just do them light. But kind of make them like they're not officially part of the answer. If you do that on the AP test for response, you lose points. So, okay, sketch a solution curve through the given points on a slope field. So this is a slope field already done. We're just trying to sketch the answer. So 1, 1 looks like it's around here. So let's label it, show that point, and then try and follow the slope field. You shouldn't end up crossing any of the slopes. If you start crossing them, that's no good. You should put arrows on the ends because it keeps going. Slope field's only shown for a snapshot of them. 0, -1 would be right here. 0, -1. And so this one, so we can have like very different kind of looking curves. So it probably goes in like this. All right. Okay. And then -1, 0 is right here. So this one kind of peels off this way. All right. Okay, so that's what we're looking for. Just label them, show it, put arrows on the ends. This was problem number 5. This was problem number 6. This was problem number 7. So should be able to do that. The next one's multiple choice. You're trying to match slope fields to their differential equations. So it's kind of like what we've been doing, but try and take advantage of process elimination. So you might say, well, when does this equal 0? Nowhere. So this one, whatever the answer is, just better not have when's it undefined. Well, that's going to be an x equals 0. So along the y-axis, you should have vertical slopes. So that kind of looks like D, right? I think that's only one. So I feel pretty comfortable going with D for number 8. This one equals 0, nowhere, equals undefined. Well, when the denominator equals 0, which is the x-axis. So we're looking for one that has vertical slopes along the x-axis, which I think is this one. I think that's the only one that looks like that has that going on. So I think this has got to be F. And you could go through and do more work to confirm it. Like, hey, these are all positive slopes up here, negative slopes down here. This should be true. When y is positive, you get positive slopes. When y is negative, well, down here, you get negative slopes. So that makes sense. When does this equal 0? Doesn't. Undefined. Doesn't. But it is positive. Always positive, no matter what, right? Always positive, because x gets squared, right? The negative means it's down here. If x is negative, it gets squared. Even x is 0 is going to be positive. We're looking for a graph that has all positive slopes everywhere. And I think the only one that looks like that is true is E, right? And when x equals 0, it has a 1 slope, which kind of makes sense with this. So you could kind of look for maybe some kind of distinguishing slope that's easy to identify. Okay, number 11, when's this equals 0? Well, that's going to be y squared equals 1, square root of both sides, plus or minus. So when y equals plus or minus 1, those horizontal lines that should have 0 slopes. And that looks like B. right? See those two chunks of horizontal line. So I think pretty safe to say B. There's another one. When's this one equals 0? When y equals negative x. So along a slanted line. When's it equal undefined? When y equals positive x. So we're looking for one that has 0 slopes along y equals negative x. I mean, we only have 2 left. So, I mean, is it this one? Do they look like 0 slopes along this line? It looks like maybe. And then undefined slopes along y equals x kind of looks like it. Those look like vertical. These look flat. I mean, looks like A. This one doesn't look like it has 0 slopes. This one's kind of like all over the place. This one, when does it equal 0? When sine x equals 0, which is when x equals 0 plus pi k. And also when sine y equals 0, which is when y equals 0 plus pi k. So we're looking at a bunch of vertical lines and horizontal lines that have 0 slopes, flat slopes. So maybe that's this one. You see this group of flat slopes, flat slopes, flat slopes, flat slopes, flat slopes, right? And then flat slopes along these horizontal lines, right? So that seems to be C. Now, next one, match these slope fields with the equation they represent. This is too easy for the AP test, but maybe I'll give you some. So we're literally looking at these and say, which slope field matches this shape? This is a hyperbola, right? Opening left, right. So it should look something like that. And I think that's B. 15, this is an exponential, so it should look like this, which I think looks like E. This one is an exponential, except that the x gets squared, so it kind of has like a reflected look. It kind of looks like a parabola. So I'm going to go with D. And this one is just a rational function, so it has a horizontal asymptote and a vertical asymptote. It looks like this, or it looks like this. I mean, specifically, I guess this one. So I'm going with A. So, I mean, it's kind of hard to see. So, I don't know. There's definitely a vertical asymptote at x equals 0. And I guess if you looked at one of these like this, you kind of see it better there, right? So there you go. Maybe you'll get some that easy on your test. You should see some kind of evidence of your thinking. Okay, even on these ones, right? I mean, I wrote stuff down. I, circled it on the graphs. Now, solving differential equations is more of part 2 of your test. But this is some good practice with it. So we've been doing a ton of these. You guys should be great at these. These are the most work probably on this test out of whatever problems, but also the most you've done more than any other kind of problem, even since last year. So separate the variables, integrate both sides. That should be an x plus c, use initial condition. So this is going to be 36 over 2 equals hold on, no. 16 over 2, negative 4 squared. 3 times 6 is 18 minus 36 over 2 is 18 plus c. So these cancel out. So c equals 8. So we're going to rewrite it. Y squared over 2 equals 3x minus x squared over 2 plus 8. I want to solve for y now. Multiply both sides by 2. So we get 6x minus x squared plus 16. Square root of both sides, plus or minus, better be in your work. And then you should decide right now if it should be positive or negative. If you plug in positive 6, you should get negative 4. That'd be 36 minus 36 is 0. Square root of 16 is 4. It needs to be negative. You got to go with the negative this time. Okay? Now, we got to figure out the domain. There's an issue right here that says that the y can't be 0. But there's also the issue here that the inside of this has to be greater than or equal to 0. Well, that's the same thing as the inside of this mean equals 0 is the same as y equals 0, right? Because that's y. So we got to solve this. I would factor a negative out and put the x squared first. Minus 6x minus 16. And set equals 0. These are easier. You don't have to keep track of the inequalities because you're not really finding this guy's domain. You're finding a single open interval. So these actually allow you to be a little lazier. Minus 8 plus 2. So x equals 8, x equals negative 2. Now, I put them on a line, not to do like a line check so much, but just to organize it. They're always going to be open dots for these. Even though this says that it can be equal 0, this up here says it can't be, and it's always a single open interval. Now, which one contains the initial condition? X equals 6 is right here. That's your domain. So our final answer is y equals the negative square root of 6x minus x squared plus 16 for the domain negative 2 to 8. You have to give the domain with your answer to the solution of a differential equation. Got it. All right, so next one, separate the variables. And it's going to be y to the negative 2, right? And we're going to increase it by 1, divide by negative 1. 6x minus 2x squared over 2 plus c. I'm going to rewrite it with positive exponents. And then I'm going to plug in the initial condition. So y equals negative 1/4. So that's going to be negative 4 equals 18 minus 9 plus c. So that's 9. So c equals negative 13. So the answer is going to be negative 1 over y equals 6x minus x squared minus 13. I want to flip both sides upside down and multiply by the negative. Okay, and then we got to figure out if there's some issues here. So we know that the denominator, by the way, another way to write this, which is a little nicer, is to apply the negative to the bottom and write the bottom in more of a standard form. But whatever, that doesn't matter. The bottom can't be 0. Up here, there's no issues. Here, this can't equal 0. So we got to figure out, can we factor that? Two negatives, and multiply together 13, add together 6. Nope, can't factor it. So we got to do quadratic formula. X equals negative b plus or minus. I'm using this version. You can use this version. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now that's going to be 6 plus or minus the square root of negative 16 over 2, which is going to be 6 plus or minus 4i. It's imaginary. So those aren't going to do anything for us. So there are no problems. So there's not really a need for even any kind of line because it's going to either be the whole line or not. And so for the domain, negative infinity to positive infinity. Or this other one. That's fine. But you guys show the work. If I don't see the work, and you just say all real is negative infinity to infinity, negative credit. Okay, now this one, this is exponential, by the way. But on this group of problems, you're going to be required to actually solve the differential equation. So even if you get like a logistic one, you're going to have to do it. Okay. So we're not going to take this approach on these. We're going to separate the variables. And we're going to integrate both sides. And we're going to plug in the initial condition. So c equals natural log of 20. So we're going to plug that back in. We're going to exponentiate both sides and use rules of exponents to split that up and get rid of the absolute value. Do plus or minus 20 e to the 10t. You got to decide if it's positive or negative right now. This better be in your work. If you plug in 0 for t, you get positive 20. So we want the positive. Now for domain, are there any issues here? Nope. Any issues up here? Nope. So your final answer is p equals 20 e to the 10t for the domain, negative infinity, positive infinity. This is where you're allowed to use this solution from that differential equation. That's what the domain is. Okay. All right, now this one, just so you know, this looks like logistic. And you could try and tweak it to see if you can make it look like that. This needs to be, remember it's ky m minus y. So this needs to be a single y. So you got to factor out a 0.2y, 0.2y, which is the same as dividing by 2/10 or multiplying by 5. So this is 100 minus y. So this is your k, that's your m. So, I mean, I guess you could, you could write the logistic for it. This is your initial condition. It would take some work, but I'm just letting you know on the test, I'm going to expect you to be able to solve this without the formula. So, now on the second part of the test. On this part of the test, I'm going to give you logistic questions. They're coming up on a later page. So that would fit into those. So the formula, you need to have this memorized anyways, is y equals m over 1 plus a e to the negative mkt. We have n, we have k. The one thing you got to find is a, and you're going to be able to find that from the initial condition. No formulas. I don't want any formulas for a. So m is 100. And so that's 100 times k is 0.2. So this is going to be 100 over 1 plus a. If you plug t equals 0 in, that's going to be a. So now you can do 20 plus 20a equals 100. 20a equals 80. A equals 4. So you can write your equation now. The equation should be y equals 100 over 1 plus 4 e to the negative 20t. That's your solution. Okay? And then not t, I guess x, because there's no t's here. The domain, there's no way this is ever going to equal 0, and there's no issues at the top. So for the domain, negative infinity, positive infinity. Okay, now, like I said, on this part of the test, part 1, I'm going to get straight out give you logistic problems, and you should use these memorized equations. But on part 2, all the differential equation ones, I'm going to expect you to be able to solve this. So let's see if we can do it. Separate the variables. Let's see. And we could just bring the whole thing over here. All right. Probably want to factor this. I think you probably want to factor out a 0.2y at least. 0.2y. That'll just make things easier. And then that would be 100 minus y. Okay. I'd probably put the 0.2 back over here. And then now we're going to have to do partial fractions. So that's one of the challenges here. So it's going to be a over y plus b over 100 minus y. So we're going to multiply through by the least common denominator. Plug 0 in first, and a equals 1 over 100, and then plug in 100, and b equals 1 over 100. So they're the same. So this is going to be 1 over 100, 1 over y plus 1 over 100, 1 over 10, 1 over 100 minus y, dy. So we're going to get 1 over 100, natural log the absolute value of y. Here we're going to get plus 1 over 100, natural log of the absolute value of 100 minus y, but this has an extra negative in it, so you're going to need an extra negative on the outside, equals the integer of the other side is going to be 2/10 x plus c. So now we got to use the initial condition to find the c value. Now let's clean this up maybe a little bit before. Log rules. I'd multiply both sides by 100. And when you multiply c by 100, you don't need to write 100c. You could if you want, but I would just write it as just a new c. And if you solve for c here and plug it back in here, you should be good. So if we plug in initial condition, which is 20 for y, that's going to be 20 over 80, and 0 in for x. So c equals natural log of 1/4. So then we rewrite it, and it's natural log of y over 100 minus y equals 20x plus natural log of 1/4. And we exponentiate both sides, and we get rid of the absolute value, plus or minus. This is going to give you 1/4 in front. Okay. Is it the positive or negative? If you plug in 0, did I lose? Something? Oh, there's an x there. Okay, you plug in 0 here, you get 1, so you get 1/4. And you plug 20 in here, you get 20 over 80 is 1/4. It's supposed to be positive. So then we're going to multiply the 100 minus y to the other side. And now it's just like nasty algebra. So this is going to be 25 e to the 20x minus 1/4 e to the 20x y. To make things easier, you might multiply everything by 4 just to get rid of the fractions. And then move this y back over here. So, and then factor the y out. So there's going to be a 4 plus e to the 20x equals 100 e to the 20x. And then you can divide both sides by that. And that's an okay answer. I mean, this could be your answer. This doesn't look like the one we wrote from the memorized equation. Because I don't know if you remember, this was what we got initially, and then we took a couple steps to tweak it. So it should be the same thing. I guess the thing you would do is you multiply top and bottom by, I think, 1 over e to the 20x. And then that would give you 100 on top, and then 4e to the negative 20x plus 1. So it's getting real close. Okay, Euler's method. You could just do we're doing tangent lines, so you should be able to just, how do you write the equation of a line? Y minus y1 equals m times x minus x1. But we're going to say y new, the new point, equals this known point, which I'm going to call the old, and then the derivative is the slope. And then x new minus x old is your delta x. So y new equals y old plus y prime old times delta x. So that's the formula. And then you can make a table that kind of organizes that. Xy, y prime, delta x. We're starting at 0, 4. We want to get to f of 1 with step sizes of 0.2. This is going to be kind of annoying. 0.2, 0.4, 0.6, 0.8, and 1. Delta x is 0.2, 0.2, 0.2, 0.2, 0.2, 0.2. I don't think we're going to need the last one. So it's going to be this plus this times this. So the derivative is x plus y, so that's going to be 4. So that's going to be 4.8. And then we add these together and we get 5. And this plus this times this. That's going to be 5.8. And then we add these together to get the next derivative, 6.2. It's going to be this plus this times this. So this is going to be 12.4, but then you got to move the decimal over 1. So it's going to be 1.24 plus 1.24. So it's going to be 7.04. So then you add these to get the next derivative, and it's going to be 7.64. Things are getting a little crazy. So this one's going to be 15.28, and then move the decimal over, so it's going to be 1.528, 1.528. Okay, we're getting there. So hopefully I've done this all right. It's going to be 8.532. No, I think I made a mistake. Oh, wait, 8.568. Okay, getting close. Now we're going to add these. It's going to be 9.368. And we're going to multiply these. That's going to be 18.736. And we're going to move the decimal point over. So we're going to add 1.8736. And we're going to get 6, 11, carry the 1 to 13 is 14, carry the 1 to 13 is 14, carry the 1 to 9 is 10. And so y1, or f of 1, is approximately 10.4416. All right. Okay, next one, table's already kind of filled out for you, so that should take a little bit of the burden off. Delta x, you can figure out what delta x is over here. It's 0.5, 0.5, 0.5. It's usually the same, but you can double check, make sure it's changed by 0.5 every time. Probably not going to need these last ones. It's this plus this times this plus this times this, so that's going to be 15 plus this times this. That's going to be 21 plus this times this. That's going to be 23. Wow. This problem made up for the terribleness of the last problem, right? I mean, come on. It's about as easy as it gets. Alternatively, you could write lots of tangent lines, and you're doing the same work, but it is going to take a while longer. Okay, next problem. This problem is like sort of a free response style problem, and you're going to get one of those on part 1. And that might be the one problem where you do need to solve a differential equation, which is what part 2 is going to be all about, but that could show up briefly on part 1. So this one says, consider the differential equation. The slope field is given. Sketch the solution curve that passes through 0, 1. 0, 1. Sometimes people do 1, 0. You guys got to know your coordinate systems. Is it x versus y second? So that looks like it's right on these tangent lines that go directly into each other. So the solution, this is a very special case. The solution, I mean, that's like a slant asymptote for any other solution on the sides, but if you start on it, you just stay on it. Okay? And then the next one says it passes through 0, negative 1, which is down here. So this one's a little more of a curve, and this one's going to approach this asymptote and shouldn't go away from it. It should look like it's going towards it, towards it, towards it, doesn't cross it, doesn't touch it. Nice and smooth. Arrows on the ends. Need arrows on the ends. Okay. All right. Let f be the function that satisfies the given differential equation with the initial condition f0 equals 1. Use Euler's method, starting at x equals 0 with step side 0.1 to approximate f.2. Show the work that leads to your answer. So this is Euler's method. It's only 2 steps. And I got to say, on the AP tests, Euler's methods, they usually only give you like 2 steps. So the whole table thing isn't as much of an advantage. So I'm just going to rewrite what we have. dy dx equals 2y minus 4x, which is where we're going to get our slopes from. We're starting at f0 equals 1 and delta x equals 0.1. And we want to get an approximation for f of 0.2. So that's the problem. I'm going to just do it the kind of the old-fashioned way, all right? So we're going to do y minus, we're going to write the equation of a tangent line. So we should probably find the slope first. dy dx at 0, 1 is going to be 2 minus 0 equals 2. So that's your slope. So it's going to be y minus 1 equals 2 times x minus 0. So y equals 2x plus 1. So f of 0.1, we're going to use this as our estimate. We'll plug it into this line, figure out what the point is on the line, and say that must be close to the point of the actual function. So that's going to be 1.2. So f of 0.1 is approximately 1.2. And we do it again. So we use this point. We got to find its derivative, dy dx, at 0.1 comma 1.2. And it equals 2 times y, 2.4, minus 4 times x, 0.4. So that's going to be 2. So, hey, it's nice. It worked out pretty nice. So y minus 1.2 equals m, which is 2 times x minus 0.1. And so y equals 2x is going to be negative 0.2 plus 1.2 is going to end up being plus 1. So that's your tangent line. So f of 0.2 is going to equal 2 times 0.2 plus 1. So that's going to be 1.4. So the estimate of 0.2 with 2 steps, Euler's method, is 1.4. So, okay. The other way is using a table. So the table, I'll show you real quick. Using the same idea, gotta know how to set it up. If you use this table and you clearly don't understand it super well, you're not going to get any points from me or the AP college. 0, 1, 0.1, 0.1, 0.1, 0.1, 0.2, this plus this times this. So y prime is 2. So this plus this times that is going to be 1.2. You got to plug these in. You're going to get 2.4 minus 0.4 is 2. This plus this times this is going to be 1.4. And that's your answer. Now, I still want the answer written nicely. F of 0.2 is approximately is the most appropriate symbol to use. 1.4. Okay? All right. C. C says, find the value b for which y equals 2x plus b is a solution to the differential equation. Now, okay, well, we're saying this is a solution to the differential equation, which means if we take this derivative, it should equal that other derivative, right? So I guess we could start with that. Y prime equals 2, right? B is just a number. So dy dx equals 2. And then we could set that equal to 2y minus 4x, which was dy dx that they gave us. So that seems to be like a solution, right? And then you're like, well, okay, cool, but how do we solve for b from that? Now look at this. We could plug this in for y, right? That might help. Let's try that out. 2 equals 2 times 2x plus b minus 4x. It definitely gets rid of the y's, but we still have x's. Well, let's just try it out. 4x plus 2b minus 4. What? The x's go away, and 2b equals 2, and b equals 1. Dang, that worked out nice. Okay, well, let's see. It's kind of fun. D says, let G be the function that satisfies the given differential equation with the initial condition G0, 0. Does the graph of G have local extremum, that'd be relative maxes or relative mins at 0, 0? If so, is the point a local max or local min? Justify your answer. So usually the way we find relative maxes and mins is with first derivative test, which is a line check. The only problem is that we don't have a way of solving, our derivative has x's and y's in it. So we're not going to be able to do a line check with this. So maybe we need to rely on the second derivative test. So let's find g prime of x. Now g prime of x equals dy dx, right? And we'll plug 0 in just to confirm. We do need to confirm it has critical points there before we can even use second derivative test. So let's see if we can confirm that. So it's at 0, 0. If you plug that into our equation for dy dx, we get 0, which means that 0, 0 is a critical point. Okay? You got to show the work for that. You got to verify it. You got to show the work for it. This is free response. Now let's go to the second derivative. Now the first derivative we already had. The second derivative, I think we got to work it out. So the second derivative of this is going to be 2 dy dx implicitly minus 4. Right? And so what's g prime of 0, 0? Well, we just found this. We could replace it with the 0, right? And so then it equals negative 4, which is clearly negative, which means that G is concave down, and the second derivative relative extreme says if it's concave down and you have critical point, that's got to be a high point. That's got to be a relative max. I don't memorize which way it is. I just remember if I just draw a picture, it'll be obvious. So therefore, G has a relative extremum and more specifically a relative, or I mean we could use their language, local, I guess we could have said local right here, local extremum, local maximum at 0, 0, since G has a critical point there, and by the second derivative test for relative extrema, the square root point, and by this with g double prime of 0 being negative, g is concave down. So I don't know, something along those lines. Okay, all right. Now for the last kind of problems that will be on your test. These ones are specifically for logistic growth. I am allowing you to use all the memorized equations. There's certain ones I don't want you to memorize, and if you use those, I'll just take off points even if you get the right answer. If you get them wrong, I'll take off even more points than getting wrong some other way. So these are logistic growth. You might write your equations down somewhere. P equals m over 1 plus a e to the negative mkt, and dp dt equals ky m minus y. I guess p, I should put p's if I'm using p's. Either way. So those are the two formulas you need to memorize. And then you need to memorize that the fastest growth is happening at the inflection point, which is half the carrying capacity. So find the initial population, carrying capacity, growth rate, that's K, that's M, that's P naught, and the time the population is growing the fastest rate. All right, so we have M here. We have, this is A, this is negative MKT. So I think we could find K next. So yeah, I don't know. I mean, A, the initial population, if you plug times 0 in here, you get 100 over 6, which is 50 thirds. That's your initial population. B, the carrying capacity, is 100. C is what I'm going to try and find right now. So I'm going to say, okay, well, negative 0.2 equals negative mk, and m was 100. So k equals 0.2 over 100. K equals, we could either say 2 1,000ths or 1/500th or 0.002. I guess any of those answers is fine. And then time when the population is growing fastest. So we know that happens at half the carrying capacity, right? So that's going to be when P equals M over 2 equals 100 over 2 equals 50. And we set it equal to our equation. And now you just got to take a few steps of algebra to solve it. I multiply that across. 50 plus 250 e to the negative 0.2t equals 100. 250 e to the negative 0.2t equals 50. Divide by 250. I'm going to rewrite this as a positive exponent. I'm going to flip both sides. I'm going to take the natural log of both sides. And then I'm going to divide by 0.2, which is the same thing as multiplying by 5. So t equals 5 natural log of 5. If I did that correct. 1/5. Oh, shoot. No, yeah, I think we're good. Yeah. All right, I had a little different answer on mine. I didn't clean it up as well, but I think it should give us the same thing. 5 natural log of 5. Oh, no. 5 natural log of 5. Why does it keep doing that? 5 natural log of 5. Yep, same thing. Not that you're going to use a calculator on this, but you got the same thing. In my work, I didn't rewrite it with a positive exponent at first, so I had lots of. It was kind of messier. Okay, so that's what we're doing. Now this one you got to realize is not in the ideal form yet. So we got to divide a 2 out of the top and the bottom to get it to that proper form. So this is your m, right? This is your negative mk. This is a. So a, p naught equals 250 over 6, which is 125 over 3. B, the carrying capacity equals 250, not 500. C, I'm going to try and find the k value by setting negative 2 equal to negative m k. So k equals 1 over 125th. Okay, D, fastest rate of growth, we're going to set the population equal to half the carrying capacity. So that's going to be 250 over 2 is 125 equals our expression 250 over 1 plus 5 e to the negative 2t. So now I'm going to multiply this over the other side. 625 e to the negative 2t. Subtract 125. Divide by 625. Rewrite it with positive exponents. That worked well for me last time. So e to the 2t equals 5. Take the natural log of both sides. Natural log of 5, divide by 2. So you could write your answer as t equals natural log of 5 over 2. You could write it as natural log of the square root of 5. The last problem, we could have said natural log of 25 if we, no, that wouldn't be 25. It would be a much bigger number. Okay, so there you go. I mean, I'm going to double check this against my answer I got when I didn't do it the exact same way in my solutions. And it's good. 0.804. Okay. And then you have a couple where they're the differential equation. So this is, remember, this is K, P, M minus P. So this is perfect. There's your K value. There's your M value. Your initial positions already been given to you. So A equals P naught equals 2. B, the carrying capacity equals 100. C, the K value equals 0.006. And so now all we have to do is D. Now to do D, I think we got to find our equation. P equals M over 1 plus A e to the negative M K T. So we got to find the A value, and that's where initial condition comes in. P naught equals 2 equals 100 over 1 plus A. So 2 plus 2A equals 100. 2A equals 98. A equals 49. So our equation is now 100 over 1 plus 49 e to the, this is going to move the decimal over 2 spots, negative 0.6t. We're going to set it equal to half the carrying capacity. And then we're going to solve 50 plus 5 times, I don't know, 5 times 50 would be 2,500, and then we're going to subtract 1, so 2,450 e to the negative 0.6t equals 100. I'm going to subtract 50. So we get 2450 e to the negative 0.6t. I'm going to divide both sides by 2450. I'm going to rewrite it with positive exponent, so it's going to be 1 over e to 0.6t. And 50 goes in this. I think that's 49, right? 1 over 49. So e to the 0.6t equals 49. We take the natural log of both sides. And then we're going to divide both sides by 0.6. So t equals, I mean, that's 3/5, so it could be 5/3 natural log of 49. I mean, that's one version of the answer. I'm going to double check it on my calculator. 5/3 natural log of 49, 6.486. That's the same answer I got the other way. All right, last one. This one, we got to get it into that mold, Kp m minus p. So I think we need to factor out a 0.2p. So dp dt equals 0.2p. Dividing by 0.2 is the same thing as dividing by 2/10, or multiplying by 10 halves, which is 5. So that's 100 minus p. So there's your k, there's your m. So A, p naught equals 20. B, m equals 100. C, k equals 0.2. And then we got to write the equation. P equals m over 1 plus a e to the negative m k t. If we put p naught in here, we get 20, which equals 100 over 1 plus a, because e to the 0 is 1. So we get 20 plus 20a equals 100. 20a equals 80. A equals 4. So then we can rewrite our equation. P equals 100 over 1 plus 4e to the negative 20t. Okay? I'm going to set it equal to half the carrying capacity, which is 50. We're going to get 50 plus 200 e to the negative 20t equals 100. I'm going to subtract 50. We're going to divide. So we're going to divide by 200. I'm going to rewrite this as a positive exponent, 1 over e to the 20t. This is being 1 over 4. I'm going to flip both sides. I'm going to take the natural log of both sides. I'm going to divide by 20. So t equals natural log of 4 over 20 is my answer. And just double checking. Natural log of 4 divided by 20 is 0.069, which is the same answer I got the other way. That's it. That's part 1 of your test, without probably the differential equation problem. So it's going to pretty much be like this without problems 18, 19, 20, and 21. Without 18, 19, 20, and 21. Those will be on part 2. Those are good practice for part 2.